Welcome back to Very Ordinary Differential Equations. In this lesson, we'll learn about exact equations. Well, we had better introduce that terminology, but it's going to take a little to build up to it. Suppose a first-order differential equation can be written in the following form. Some function of x and y plus some other function of x and y times y prime is 0. In other words, some function of x and y plus some function of x and y dy dx is 0. Now, what's important to pick up here is that the only place you see a y prime can be factored out of some other expression. So you don't have anything like y prime squared or divided by y prime, anything like that. Function of x and y, function of x and y prime, 0. Now, from other areas of math, it follows that this is equivalent to either of the following two things. M of xy dx dy plus n of xy is 0, or, much more frequently seen, m of xy dx plus n of xy dy is 0. Now, that last line, m of xy dx plus n of xy dy equals 0, is not just taking this line here and multiplying by dx. Dx isn't really a number, you can't just multiply by it. But this is an expression that arises in multivariable calculus. It is justified, and it's written like this very often. So we can have any of the following forms. M of xy dx plus n of xy dy is 0. This will be the most common. Or you could have dy dx on the second term, or you can have dx dy on the first term. Such a differential equation is going to be called exact if the derivative of m against the variable y is equal to the derivative of n against the variable x. Okay, so in this first expression here, which is how we will most often see it, you take the derivative of this function against y and the derivative of this function against x. If those two derivatives are equal, it's called exact. Now, these are partial derivatives from multivariable calculus because we do have two different variables floating around, x and y. Now, let's suppose we do have an exact differential equation. So here's our differential equation in the form we'll most often see it. M of xy dx plus n of xy dy is 0. Also, the partial derivative of m dy is equal to the partial of n dx. Now, by Clairaut's theorem, with some other technical assumptions that we really don't want to get into, there must be some other function, capital F, of both variables x and y, so that m is its x derivative and n is its y derivative. Pay attention to what variable occurs where. M is the function with dx, n is the function with dy. If the m y derivative equals the n x derivative, then m is the x derivative of f and n is the y derivative of f. So if we have this scenario, how are we going to solve our differential equation? So suppose we have m of xy dx plus n of xy dy is 0, where dm dy equals dn dx. Therefore, there must be some function capital F so that m is its x partial derivative and n is its y partial derivative. The differential equation can then become, and this uses the multivariable exact differential, which is why these are called exact differential equations. It becomes the differential of f is 0. Okay, so if m is the x derivative and n is the y derivative, then x derivative dx plus y derivative dy is what's called the exact differential of f, and we have that equal to 0 here. Now, if the exact differential of a multivariable function is 0, it follows that that function must be constant. And conversely, if f of xy is a constant, with its x derivative being m and its y derivative being n, any function we can find like that will also be a solution to the differential equation that we started with. So if a differential equation is exact, what we need to do is find a function f so that the x partial of f is this function here, and the y partial of f is this function here. That's under the assumption that the y partial of m equals the x partial of n. So how are we going to find such a function? Suppose you manage to verify that this differential equation is exact. In other words, dm dy equals dn dx. Okay? Therefore, solutions must be of the form f of xy equals a constant, where the x partial of f is our function m and our y partial of f is our function n. Well, how are we going to find that function? And then just declare f of xy is constant, there's our solution. It's a successive sequence of integrating, differentiating, and integrating again. Okay, so first, since the m function is the x partial of f, it follows that if I integrate m against the variable x, that must be the function f of xy. So take this expression m of xy dx and integrate it, and it's already telling you what variable to integrate against. That's going to give you f of xy. However, you're going to get a constant of integration, as you always do. But the variable of integration was x, which means that y is considered to be a constant. Okay, if you're only integrating against the variable x, you are momentarily treating y as if it's a constant, and that means your constant of integration can actually be a function of y, because as far as x is concerned, that would still be a constant. So in other words, when you perform this integration, you get some sort of x antiderivative here, plus a constant of integration that actually can depend on the other variable y. Now, if this is f of xy, take d by dy of all of this. Having just integrated dx to get this expression, take d by dy. Then what you'll end up with is, by assumption, df dy is n, but taking d by dy of this expression gives me dg dy plus phi prime of y. This is just a one-variable calculus derivative because I took the y derivative of a function that only depended on y. Then you can solve this for phi prime of y, integrating back to get phi of y, and any solution will do. You'll get a constant of integration, but you've eliminated all of your variables, so it really is just a constant, and that's how you get your function f of xy. So in summary, what is our technique? Given a differential equation of the form m of xy dx plus n of xy dy is 0, first check to see if it's exact or not. Take the y partial of m and compare it to the x partial of n. If they're equal, it's exact and you can proceed. If they're not equal, it's not even an exact equation. So if those are equal, you need to find some capital F so that its x partial is m and its y partial is n. Now, how do you do that? Integrate m of xy dx to get a possible antiderivative, but the constant of integration can depend on the variable y. So when you integrate this against dx, you'll get some function plus an unknown function only of the variable y, and that should be f of xy. Now take d by dy of all of this, and on the one hand, d by dy of f will be n. On the other hand, you get this partial derivative plus this actual derivative, and solve it for phi prime. Then anti-differentiate phi prime of y dy. Now this is a function that depended only on y, and I'm anti-differentiating against y, so the constant of integration here will be a genuine constant. And then you can find f by taking your choice of phi and plugging it back in here. And now you'll have f of xy is this function you found plus this other function you found. And finally, solutions to the differential equation will be of the form f of xy equals a constant. Now we'd better go ahead and see all of that in action. So let's find all solutions to 2xy plus 3x squared y cubed dx plus x squared plus 3x cubed y squared dy equals 0. Well, first we should verify the function is exact. So take the y partial of the first term, the thing that's being multiplied by dx, and compare it to the x partial of the thing multiplied by dy. So first we take d by dy of the thing that was multiplying dx. Treating x as if it were a constant and taking a y derivative, we have constant times y. The derivative of that will just be the constant. 3 constant y cubed. The derivative of y cubed is 3y squared, so I get 3 times x squared times y squared, or 9x squared y squared. So pretending that x is a constant and taking a derivative where y is the variable gives me this. But then I need to compare it to taking this other term, taking d by dx, so now pretend that y is a constant and take the x derivative. Well, the x derivative of x squared is 2x. The x derivative of 3x cubed y squared is 9x squared y squared. So those are exactly equal. So the equation is exact and we can proceed. Now that we know the equation is exact, we integrate one term against the correct variable. So we take that first term, 2xy plus 3x squared y cubed, and I anti-differentiate against the variable x that it was already being written with. Okay, anti-differentiating 2xy gives me x squared y. Anti-differentiating 3x squared y cubed gives me x cubed y cubed, and the constant of integration is actually a whole function that can depend on the other variable y. So whatever f of xy is, it should be x squared y plus x cubed y cubed plus terms that only involve the variable y but no longer involve the variable x. So now I take a y derivative and compare it to the capital N. So I take a y derivative of what we just found. So I need to take a y derivative of x squared y plus x cubed y cubed and this unknown function phi. And we end up with x squared plus 3x squared y plus phi prime. But that should all be equal to capital N, which is x squared plus 3x cubed y squared. So we have x squared plus 3x cubed y squared, this is capital N, equals x squared plus 3x cubed y squared plus phi prime of y. This was the derivative of what we had found up here, d by dy specifically. Notice that in this case, phi prime of y can easily be solved for. It's just 0. So we already determined that f of xy must be x squared y plus x cubed y cubed plus an unknown function of y, and whatever that function of y is, its derivative is 0. Well, therefore, we can choose any constant to be phi of y. Let's just use 0 itself. Anything whose derivative is 0 would be good enough. Then I go up here and I replace phi of y with our choice of phi of y equals 0, and we get capital F of xy is x squared y plus x cubed y cubed. Therefore, all solutions of the differential equation are given by f of xy equals a constant. So there are the solutions to the differential equation we began with. Let's go ahead and take a look at a second example. And this one looks a bit nastier. E to the y plus y cos x plus 3 dx plus x e to the y plus sine x minus sine y dy all equals 0. Well, step 1 is again verify that it's exact. Take a y partial of the thing multiplied by dx, compare it to the x partial of the thing multiplying dy. So first let's take d by dy of e to the y plus y cos x plus 3. Now, treating y as a variable but x as a constant, the derivative of e to the y will be e to the y. The derivative of y times constant is that constant, and the derivative of 3 is just 0. I now need to compare this to d by dx of this term here. Since I'm doing d by dx, x is the variable and y is a constant. Well, if y is constant, e to the y is a constant. So x times constant, the derivative is just constant. The derivative of sine x, cos x, and if y is constant, the sine of y is a constant, so its derivative is 0. So lo and behold, they do agree. We do have an exact equation, and we can attempt to solve. So we integrate one function against its proper variable. So we can go ahead and integrate e to the y plus y cos x plus 3 against x. Since I'm integrating against x, y is pretending to be a constant. What's the integral of constant? Constant times x. Constant times cos x integrates to constant times sine x. Constant 3 integrates to constant x, and my unknown constant of integration is actually a function of the other variable, y. So here is capital F of xy. It's x e to the y plus y sine x plus 3x plus something that only depends on the variable y. So that's what we've determined so far. Capital F of xy must look like this, but we have an unknown function of y. So we take a y derivative and compare it to that function n. So on the one hand, here's n of xy taken from up here, x e to the y sine x minus sine y. It should be equal to d by dy of capital F, all of this stuff we just found. So we're taking d by dy, which means x is a constant. What's the derivative of constant times e to the y? Just constant times e to the y. What's the derivative of y times a constant? Okay, if x is a constant, sine x is just some number. Number times y, the derivative is whatever that number is. Well, if 3x is a constant, its derivative is 0, and whatever this function phi is, its derivative is phi prime. So overall, x e to the y plus sine x minus sine y equals x e to the y plus sine x plus phi prime. So we determine that phi prime must be minus sine y, and therefore, phi of y is cosine of y, plus any actual constant, but it doesn't really matter which choice we make, so we'll just take the constant here to be 0. So we've now determined that capital F of xy is x e to the y plus y sine x plus 3x plus phi of y, but we just determined that phi of y could be taken to be cosine of y. So here is our function f of xy, and therefore solutions to the differential equation are just f of xy equals a constant. Next up, let's do another example. Here's an initial value problem. We have an expression dx plus another expression dy equals 0 with the initial value that y of 1 equals 1. As before, check that it's exact. So we take d by dy of the first expression. If x is a constant, what I really have is e to the x squared minus variable squared. Okay, and I end up with the chain rule spitting out a minus 2y, so we get minus 4xy e to the x squared minus y squared. What's the derivative of cosine of constant minus y? It's going to be negative sign, but the chain rule spits out another minus sign, so we get plus sign of x minus y. We now need to compare this to the x partial of the other term. So now we're treating x like a constant, so chain rule is going to spit out a 2x, negative 4xy e to the x squared minus y squared. D by dx of this is just going to be plus sine of x minus y, and d by dx of 8y is just 0. So they do agree, it is exact, we can proceed. Integrate one function against the appropriate variable. So we take that first expression and we integrate dx, and work it back to be e to the x squared minus y squared plus the sine of x minus y, plus a constant, but that constant can actually depend on the variable we haven't attacked yet. In other words, it's some phi of y. We've determined so far that capital F of xy must be e to the x squared minus y squared plus the sine of x minus y plus some unknown function, but this unknown function phi can only depend on the variable y. So we're going to take d by dy and compare it to capital N. Okay, so capital N of xy should be d by dy of f of xy. On the one hand, capital N is this expression up here, and on the other, if I take d by dy of all of this, we get minus 2y e to the x squared minus y squared minus cos of x minus y plus phi prime of y, where this derivative we really don't know because we didn't know this function phi. Notice everything cancels except for the terms that only depended on the variable y. If you're doing this correctly, if the equation was exact and you haven't made any mistakes, this should always be what happens. Okay, when you solve for phi prime of y, if there are still x's left in the mix, then something went wrong. We now have phi prime of y involves only the variable y. Anti-differentiate, get 4y squared, plus any constant, but it really doesn't matter which we pick, so we may as well go with 0. Now that we know that phi of y can be taken to be 4y squared, we simply take that back up here, and we have our function capital F of xy. So capital F of xy is e to the x squared minus y squared plus the sine of x minus y plus 4y squared. And solutions to our differential equation are of the form capital F of xy equals a constant. So here we have it, capital F of y equals a constant. We also see, by the way, why the constant of integration from phi wouldn't really matter. It can be absorbed into this constant over there. We have to take care of our initial value problem, however. When x is 1, we're supposed to get out y is 1. So plug in x and y both equal to 1. You'll end up with e to the 0, that's a 1, plus the sine of 0, that's a 0, plus 4, that's just 4, equals c, so c is 5. Therefore, the solution to our differential equation is given by e to the x squared minus y squared plus the sine of x minus y plus 4y squared equals 5. So what have we learned? An exact differential equation is something of the form m of xy dx plus n of xy dy is 0. And you also have to have that the y partial of m equals the x partial of n. If those two things aren't equal, you don't have an exact differential equation. But if they are equal, there has to be some function capital F so that its x partial is m and its y partial is n. Solve for this by doing the integrate, differentiate, integrate sequence of steps. And once you have this function capital F of xy, solutions to the differential equation are the curves f of xy equals a constant.